Stan Gibilisco here to illustrate for you one of the very significant uses of the operational amplifier, also known as the op amp, which I described functionally in a recent video. An operational amplifier has a symbol that looks like this. Two inputs, one of them called the inverting input, which produces output that's not 180 degrees out of phase, but in phase opposition or inverted with respect to the input. So if you put a signal in here, it comes out upside down here. If you put a signal in here, the non-inverting input, it comes out right side up, but amplified. Let's suppose that you decide to make an amplifier and you don't want it to invert the signal, so you apply your input signal to the non-inverting input like that, and you get a certain amount of output that depends on the value of this resistor right here, the value R of that resistor. The higher the value of the resistor, the lower, the greater the gain of the op amp, and the more output you will get. If you want to reduce the gain more and more, you would make this resistance smaller and smaller, thereby providing more and more negative feedback to this system. Now, one of the interesting things about this circuit is that it is frequency independent because this resistor has no reactance. So whether it be, say, an audio frequency of 50 hertz or 100 hertz or 300 hertz or 700 hertz or 7,000 hertz, the gain of this amplifier will be the same regardless of the audio frequency. But suppose you want to make what is known as an audio frequency low pass filter. That means that the gain of your op amp should be greater at lower frequencies and less at higher frequencies, thereby creating a curve, a response curve. If you put frequency on the horizontal axis and output on the vertical axis, you will get a curve that looks something like that. As the frequency goes up, the gain goes down. How can you do that with an operational amplifier? Well, actually, it's very simple. You can place a capacitor in parallel with this resistor. Now, the exact values of the resistor R and the capacitor C will determine where this frequency drops off the steepest. However, I'm not going to talk about that here. It's rather complicated, but you can find formulas to calculate that on the internet, plenty of them. Just put this in as a phrase, Amp Lowpass Filter, and you will come up with at least a couple of good technical articles on that subject. However, the theory by which it works is this. The resistor, as I have said, does not affect the gain as the frequency changes, but the capacitor will. As the frequency goes down, the reactance of this capacitor will increase. So this capacitor-resistor combination will offer more opposition to the signal as the frequency goes down. As the frequency goes up, this capacitive reactance will decrease, meaning that the RC circuit here will provide more and more feedback. So, as the frequency goes down, the negative feedback, the amount of negative feedback, also goes down and the gain goes up. As the frequency goes up, the amount of negative feedback increases and the gain goes down. That's a low-pass filter, and that's the theory by which this whole system works. Once again, the frequency where the slope is the steepest here, where the drop-off is the most significant, is going to depend on the resistance R in ohms and the capacitance C in farads, or you might say kiloohms and microfarads or something like that. And formulas are available on the internet to calculate that, so you can design your own op-amp low-pass filter. Pretty simple, eh? And no big old bulky coils involved at all. Just a resistor and a capacitor and an operational amplifier. Stan Gibilisco, signing off for now. Until next time, so long.